Welcome to Algebra 2. We got section 4.3, dividing polynomial functions today. All right, so for our introduction, dividing polynomials is really very little difference from dividing numbers. But in order to get a true sense of this, what we need to do, first of all, is revisit long division. So this is from your third grade classroom. So problem number 1, we're taking 34 divided by 3, and you can see they say write your answer in the form of Q plus R over D. That stands for quotient plus the remainder over the divisor. So for number 1, we're going to set up 34 divided by 3 just like we did in third grade. 3 goes into 3 one time. 1 times 3 is 3. Then we subtract the 2 and drop down the next number in line. 3 goes into 4 one time. 1 times 3 is 3. Subtract them and get a 1. That is our remainder. And this 11 is our quotient. So our answer is 11 1/3. Let's try number 2. 165 divided by 9. And 9 goes into 1 0 times. 9 goes into 16 one time. So you can see I'm in the tens column now, keeping everything organized vertically. 1 times 9 is 9. Take the difference. 16 minus 9 is 7. Drop down the 5. 9 goes into 75 8 times. 8 times 9 is 72. Take the difference, and our remainder is 3. So our answer is 18 3/9, which we can simplify 18 1/3. Okay, number 3, just to get more of a feel for these placeholders, we've got 1003 divided by 6. 6 goes into 1. No, can't do that. 6 goes into 10 one time. 1 times 6 is 6. Take the difference and drop down the next digit. 6 goes into 40 6 times. 6 times 6 is 36. Drop down the next in line, 43. 6 goes into 43 7 times. And we get a remainder of 1. 167 1/6. So you can see that each time our divisor, that R over D, the remainder is just the end of all of our subtractions taking place under the division bracket, and then the divisor, the bottom of that fraction, is just coming from what we're dividing by. We're going to keep up or keep track of that pattern. For the second part of our introduction, we're going to simplify the expression, and here you can see that our denominator is a monomial. We don't see like two terms added together or subtracted. So in this case, what we're going to do is think about this as being addition and subtraction all over a common denominator. So we don't have to write all this out each time, but it's helpful to think of it this way. What if we undo all of that common denominator, addition and subtraction? Now we've got 3 individual fractions that we can simplify on their own. So I've got 6 over 3 is 2. I got x to the 4th. I'm dividing away one of those x's. That's x to the 3rd. And then there's a y in the denominator that does not cancel from the numerator, so it stays. Plus 12 divided by 3 is 4 over 1. X cubed over x squared is just 1x when we divide the 2 x's out of the 3. And then y squared. And there was no denominator there. Everything divided out. 18 divided by 3 is 6. X squared divided by x is 1x. And then y divided by y, those cancel out. It's just a 1. So here is our simplified expression. Okay, so as you get better at this, as long as you remember that you're dividing everything in the denominator, you're using that to simplify each term, you can really bypass this step if you would like. It's easy to make careless mistakes doing this, but it is something that hopefully by the end of this you'll feel confident doing in your head. So number 2, let's start with this first term. I've got 20 divided by 4, 5 over 1, c to the 4th over c, that's c to the 3rd, d squared, and I'm dividing a d out from that, that's 1d, and f divided by f. There's our first simplified term. Now that denominator doesn't go away, right? We need to use that on the second term here as well. So I've got negative 16 over 4, that's negative 4, c over c, d over d, f squared over f, that's just an f. And now the last term, 4cdf divided by 4cdf, anything divided by itself is 1. So 2 somewhat different concepts, but one deals with simplifying, and hopefully we can recognize when we have this common denominator situation as opposed to when we have long division necessary. And the questions do a pretty nice job of laying that out for you pretty clearly. All right, our key concepts for today. Long division can be done with polynomial expressions as well, and the process is very much the same. We'll let the examples kind of work us through that process. There also is a streamlined way to divide polynomials through synthetic division. This is just a pattern that gets rid of all the variables and focuses simply on the coefficients instead. We will make a little note here that synthetic division works best when you're dividing by an expression that is like x plus 3 or x minus 2, when it's 1x and then some number. Otherwise, long division tends to work a little bit better. It's a little bit easier to understand. Okay, regardless of which division method we choose, the remainder theorem states that the remainder, when dividing out a factor of a polynomial, produces the same value as evaluating the polynomial with the solution from that factor. So in this case, if we were to divide a polynomial by x plus 3, the solution out of that factor is x equals negative 3. Whatever we would get as the remainder is the same thing we would get as if we had plugged in a negative 3 to begin with. Okay, so once you get a feel for the pattern of synthetic division, you'll get to see how fast this is. It makes it much easier to do work like this by hand. Okay, example 1, divide using long division. Well, we're going to set this up just like we set up the division problems in our introduction. One thing we want to be sure of, though, is that we are setting up what's being divided, that it is accounting for every single x value. So I've got 3x squared, I've got a regular x, then I've got a minus 5. Say there were no x term there, I would write plus 0x in there just to hold place. Remember, we had everything lined up nicely in columns when we did our introduction. The same thing happens here, so it's nice to have those placeholders. All right, the question we're trying to ask ourselves is, what do I need to do to make this x value, the leading term of my divisor, make that perfectly match this 3x squared? Because I want them to eliminate eventually. So in order to turn this x into a 3x squared, I would need to multiply by 3x. Okay, so 3x, that goes in the x column of my quotient. And then just like long division, we have to multiply that by what's out front. 3x times x is 3x squared. 3x times negative 5 is negative 15x. Okay, and just like with our introduction, we subtract the 2, but I like to think of that as switching the signs and adding, because there is distribution taking place. The 3x squareds cancel like we wanted them to, and the negative 14x and 15x combine to make 1x, and we drop down the next term in line. What do I have to multiply x by to get x? It's just a positive 1. 1 times x minus 5 is x minus 5. Switch the signs and add, and we get a remainder of 0. So our solution is 3x plus 1. Okay, we can also use long division if we're dividing by something that's not just a binomial. So here we're taking one trinomial divided by another, and that works just as well. I've got 4x to the fourth. Ooh, there's no x squared terms, or x cubed terms either. 0x cubed plus 0x squared plus 5x minus 4. And you can see there, it lays out all of those exponents, even though I don't see them in what I'm dividing by, or in what I'm dividing. I want to make places for those in my quotient up above. All right, we're concerned about the lead term. What do I multiply x squared by to get to 4x to the fourth? Well, that would be 4x squared. So I put 4x squared in that appropriate column, and then we distribute it. 4x to the fourth minus 12x cubed minus 8x squared. Switch the signs and add. You can see the x to the fourth cancel. Those are the ones we wanted to cancel. We get 12x cubed and 8x squared, and we drop down the next one in line, plus 5x. What do I multiply x squared by to get 12x cubed? That would be 12x. 12x times x squared, there's our 12x cubed. 12x times negative 3x is negative 36x squared. And 12x times negative 2, negative 24x. Switch the signs and add. The x cubes cancel. We have 44x squared and 29x. Drop down the next one in line. What do I multiply x squared by to get to 44x squared? Well, positive 44. 44 times x squared, 44x squared. 44 times negative 3, negative 132. And 44 times negative 2, negative 88. Switch the signs and add. We get 161x plus 84. And you can see here I'm at the point where I can no longer multiply x squared by something to get 161x. So this is our remainder, and how we would write that solution is 4x squared plus 12x plus 44 plus 161x plus 84 all over my divisor, x squared minus 3x minus 2. All right, example 3, divide using synthetic division. All right, well, if we are given a factor like this to divide out, what we're going to do with synthetic division is we're going to set up a little box and a bar here. And this is just the pattern that helps organize our numbers. So if you're wondering why that is the way it is, it's just to organize. And what goes into this little box, that's going to be kind of like coming from our divisor. And here our divisor is x minus 2. The solution out of that factor is x equals positive 2. So positive 2 goes in the box. Okay, now in line with this 2, we're going to set up synthetic division by placing the coefficients in order along the way. Now, we've got x squared and then a regular x and then a constant. We may need zeros as placeholders, but for now we're fine. We've got all of our exponents covered. So I've got 4x squared, negative 13x, and negative 5. In line with this negative 5, I like to put a little separator there because our remainder will show up down in this corner. How the process works, and this is really not, you'll see a lot of arrows and a lot of multiplying and adding together. That's exactly streamlining the process of long division. So the first step is to drop this 4 down. The first number in our line goes straight down. This is where our quotient will appear. And once that 4 has been dropped down, I look in the box and see a 2. I take 2 times 4 and get 8, and that fills the spot for the next addition. Okay, now we add down this column. Negative 13 plus 8 is negative 5. 2 times negative 5, negative 10. Again, referring to that 2 in the box. And then we add. Negative 5 and negative 10 is negative 15. So the answer here, this is my remainder, so that ends up going over the divisor of x minus 2. And then this 4 and negative 5, well, this is a constant. This would be my x term, and if I had more numbers going this way, I would have x squared, then x cubed, then x to the 4th, and so on. So the answer, again, looking down here in this quotient part, I've got 4x minus 5, and then negative 15 over x minus 2. Okay, that is our solution. Now let's say we wanted to check this. If we wanted to conduct a check, which may or may not be required, x minus 2 times 4x minus 5 minus 15 over x minus 2. It's just the distributive property, distributing this x minus 2 to everything. Now let's see what we get. So 4x times x minus 2 minus 5 times x minus 2, and then minus, well, 15 divided by x minus 2 times x minus 2, that's just going to be a 15. If we distribute, combine like terms, you'll see that we get right back to what we were dividing away from in the first place. So it doesn't take terribly long to check, but again, the multiplication is a nice way to check the division that we've done. Do we get back to where we started? All right, let's see if we can't set up example 3 here. So in the box, we've got the solution of the factor x plus 5. That would be a negative 5. And how I'm getting that number is I would just set that x plus 5 equal to 0 and solve. Obviously subtract 5 from both sides. Then I've got 1x to the 4th, 4x to the 3rd, 0x squared. That's important. We did not get the correct answer if we did not have that placeholder. Then 16x and minus 35. Okay, the last column will end up with the remainder, so I put a little separator there. And then we run through the pattern. Drop the first number down, 1. Multiply by what's in the box. Add down that column. Multiply by what's in the box. Add down that column. Multiply by what's in the box. Add down that column. Multiply by what's in the box. And add down that column. So my solution now is going to be 1x cubed minus 1x squared plus 5x minus 9. And then my remainder of 10 plus 10 is put over the divisor x plus 5. And if we wanted to check that again, we could just multiply this by x plus 5 to undo the division, see if we get back to where we started. All right, example 4, use synthetic division and the remainder theorem to evaluate the function. Now realize that what we're going to find is actually f of negative 4. Right? They want us to take this function and see what happens when x equals negative 4. So this is what evaluating means. We're going to find something equivalent to that, but they want us to use synthetic division to do that. So we set up our box. Notice that I do not have a factor that I'm dividing by. I have a solution. Now we do not need to change the sign. It's just that negative 4 that goes in. I got 1x cubed, 1x squared, negative 3x, and positive 9. Did not need a placeholder. And then here, this remainder, that's why that separator again is so nice, that will be our answer. So let's run through the pattern, drop down that first coefficient, multiply by what's in the box, add down the column, multiply by what's in the box, add down that column, multiply by what's in the box, add down that column. So the answer should be negative 27. Now, I hope we're a little skeptical. Like, oh, I don't know if that really works or not. Let's just see what happens if we actually plugged in f of -4. Obviously, if this were much bigger of a polynomial, we'd have a tough time doing that. But if I have -4 to the third plus -4 squared minus 3 times -4 plus 9, do I end up with that -27? -4, all that to the third power is -64. Plus -4 squared, it's going to stay a positive 16, plus 12, plus 9. That's -64 plus 28 plus 9, 37, which is -27. We combine those together. So it checks out. The remainder theorem works. Example 5, the profit P in millions of dollars can be modeled by the function P of X, given here where X is the millions of DVDs produced. Use synthetic division to show the company yields a profit of $96 million when 2 million DVDs are produced. Okay, so the profit is in millions. The X value is in millions. So really what we're trying to find is P of 2, right? Because that means plugging in 2 million. And I'm hoping to show that P of 2 equals 96, representing the $96 million. Now, if I want to use synthetic division, they give us a solution for an X value, an input, a 2. So that goes in the box. We've got -6x cubed, 0x squareds, 72 x's, and 0 for a constant. So we have those placeholders there. And then our separator to find the remainder. We'll drop down that -6, multiply by what's in the box, add down that column, multiply by what's in the box, add down that column, multiply by what's in the box, and add down that column. Hey, our remainder ended up being 96, just like what we were trying to show. Now the question goes on and says, is there an easier method? So we need to show that P of 2 equals 96. Was synthetic division actually the easiest way to do this? Well, if we were to just calculate P of 2 by plugging it in, then what we get is -6 times 2 cubed, which is -6 times 8, -48, plus 72 times 2, 144, and we also get 96. So they just want you to evaluate, like, oh, we were told to use synthetic division. Would that be easier than this other one? How do you make the call? It's kind of to help you determine your own solving strategies. If I were just given this question and told to show that $96 million is earned when 2 million DVDs are produced, I probably would have opted for this one because it's such a simple function. If this were more complex, synthetic division would be much, much easier. So I think they just want you to think that through for yourself. Here's a look at your assignment for section 4.3.